Hello, everyone. Welcome to our first lecture on a new course, Design of Concrete Structures. I'm Murtaza, and I'm going to be your instructor through the course. There might be 24 lectures, and each lecture would be specifically related to the topics of this book, um, the design of concrete structures, the 16th edition by David Darwin and Charles Dolan. We might also use another book as a resource, and that is called Reinforced Concrete Mechanics and Design, 7th edition. If you have these books, then you are ready to go, and it's easy to follow the lectures. If you don't have the books, I recommend you to get the books first and then follow each lecture chapter by chapter, and also read the book. We are going to start the first lecture, and the first lecture today is an introduction. So basically, the first topic is concrete, reinforced concrete, and pre-stressed concrete. The question is, what is concrete? Basically, everyone is familiar with the concrete, and concrete is a construction material, basically a composite material. It is composed of aggregate, generally sand and gravel, and they are chemically bound together by hydrated Portland cement. So the hydrated Portland cement means that water reacts with the cement chemically, and it bonds these sand and gravels together, making a solid structure or a solid member. And this another definition for concrete is that is like a stone, and it is obtained by permitting a carefully proportioned mixture of cement, sand, and gravel, or other coarse aggregate, and water to harden in the form of the desired structure. As you see in the picture, water is added to cement, and these two reacts chemically, and then it basically bonds the aggregates together, and there might be sometimes air bubbles inside these aggregates where the water and cement can't enter spaces and minor bubbles, and it all together makes the concrete. As you see, the desired structure might be columns, beams, floors and slabs, stairs, walls, foundations, and different types of construction elements. And therefore, we say that these materials should be proportioned carefully in order to get the desired properties of the concrete. Basically, we see at the history of the concrete, lime mortars were used around 1200 to 6000 before Christ in Crete, Cyprus, Greece, and Middle East. So, sorry, it has a very long history, and it has been used for centuries. And basically, cement and water reacts, as I said, they react chemically to bind the aggregate particles into a solid mass. And the water-cement ratio determines the workability of the concrete. Once the water and cement are mixed, basically, there is a unique proportion of the water that is needed to react chemically with the cement. Any other addition to this ratio determines the workability of the concrete. So the more water-cement ratio, the higher the workability of the concrete is, and therefore changing the proportion and the type of ingredients change the properties of the concrete. So two major factors: one, the proportions, and another parameter, which is the type of the ingredients, is very important in determining the properties of the concrete. The type of ingredients basically means that the type of cement that we use, the water, and it's recommended that we use clean water. But if the water has chemicals or any other ingredients, any other elements, then it also affects the desired properties. Finally, the properties of the aggregates is very important. And when we come to the aggregates, basically the types of the aggregate and the size of aggregates are very important factors. Another factors that basically shapes the properties of the concrete is the humidity level. If the environment humidity is high, then it means that there is a high amount of water and that the concrete absorbs during the day and night, and it basically changes and affects the properties of the concrete. And if the temperature is very high, and then we need more water to the concrete so that it doesn't evaporates quickly, as we know that these chemical reactions, chemical bond between cement and concrete takes time. Therefore, we need to maintain the concrete weight for about 28 days long so that it gets the final or basically the maximum desired strength. And the type of admixtures that we use, we call them additives, also affect the properties. There are various types of admixtures that we mix with these essential ingredients of the concrete, and it changes the workability and the strength and the other properties of the concrete. The curing, as I said, is also important. We need to maintain the concrete moist and basically and to keep it all the time moist so that it reacts chemically and it gives the maximum strength in 28 days that is recommended. And that mixtures we use are could be plasticizers, air entertaining agents, and silica foam or fly ash. How we basically prepare concrete and how we use the concrete is it might take some stages and the process. First, we need to prepare the site. We need to prepare, for example, beams or columns, slabs, foundations, any type of elements that we want. First, we need to prepare the forms, and if it is on the level, on the ground, we need to level the ground. We need to do soil compaction as well as all the form work and lay out the reinforcement in the desired lengths and widths and sizes. We also add access points underneath if there are any pipes, any utilities that we need to have in passing through the concrete, and we need to lay those first, and then we mix the concrete basically proportionally and by the weight and according to the project specification. We determine the size of the aggregates, the type of cement, and the proportions in order to get the desired specifications. We also determine the workability of the concrete doing the SLAM test. There are codes and standards that we use in order to get the desired specifications and properties of the concrete. After the design mix design is made and we have already mixed these materials and ingredients, then we transport the mixed concrete to the site using either tracks, and it should be transported without a delay, and there are specific limits and duration time, for example, half an hour to maximum 1 hour, so that these concrete should be transported onto the site in order to have the desired concrete. After transportation, we power the concrete in those molds and formworks using wheelbarrow, pumps, pipes, and shovels. And we want to basically power each corner, each space, and with the desired height. So the height of those elements are very important. Then we fill the voids using vibrator and the level, and then level the surface. The amount of vibration is also important, and we do not have to vibrate a lot because it segregates the elements, and bigger aggregates goes down, and then the water cement it just blows up on the surface. Properties change and different locations, and if we use vibrators more than the desired amount, then these properties variation might be higher, and therefore there is a limitation on the use of vibrations. After leveling the surface, then we use tools to finish the surface as required. Some surface of the concrete, sometimes it needs to be quite smooth. Sometimes, for example, if it is the driveway, then it needs to be a bit rough. It should not be slippery. After we are done with the finishing, then we try to cure the concrete, try to maintain it moist, and also avoid evaporation. During this time, we also get a quality control in order to check whether our poured concrete has the desired specifications, the desired compressive strength, or if it meets those criteria in those specifications, then it's fine. Otherwise, we might need to either replace the concrete, or we might need to add another layer or any other methods and ways in order to get our desired strength and specifications. So this is all about the process. What are the main properties? As I said many times, that we need to have the desired outcome, the desired properties for the concrete. The main properties of concrete are they are fire and weather resistant, and it is unique compared to other construction materials like wood, for example. The concrete structures, concrete elements are fire and weather resistant, and therefore there is not any, for example, concerns regarding the fire and the weather. There is, for example, high moisture, there is a lot of water around. We are not worried about the destruction of elements, and it is quite durable. It stands with vibrations, weathering, as well as chemical attacks. And one thing about concrete is that can get the desired shapes. We can make the form easily, and then we can get the desired shapes. We might have various shapes of columns, beams, and other elements. And another fact is that it is affordable in most of the regions, in most of the countries. So aggregates are available, water is somehow available, and cement is also available in most of the places. And therefore, it is one of the most affordable construction materials. And it has quite a high thermal mass. It absorbs and stores heat. And in places where it's cold, for example, in northern hemisphere, or in places where the temperature is quite low, this higher thermal mass means that once we hit our structure or room, for example, and its thermal mass is high and it doesn't get cold quickly. And also it has quite high compressive strength, and therefore it's very good for building columns, arcs, and foundations, as these members carry a quite high amount of compressive loads, and therefore building these elements are essential in the buildings, and using concrete is also important. Even in the woody structures, we of course sometimes use concrete for the foundations, as it is also fire and weather resistant, and it has quite high compressive strength as well. Another factor which degrades the use of this concrete alone is that it is quite brittle and it has low tensile strength. Let's go to the reinforced concrete. In the previous page, we said that concrete is brittle and it has quite low tensile strength, and therefore it can't withstand tensile forces and tensile loads. And elements like beams, slabs, which are most of the times subjected to the tensile loads, and it has to withstand these concentrated and tensile forces and like shears or axial loads. Therefore, we need to basically find a solution for these. And many years ago, like in 18th century, people found that we can use steel bars as a reinforcement, and it is embedded to the concrete, mostly superior to the pouring concrete, in order to increase the tensile strength of the concrete. The combination of the steel and concrete material is known as reinforced concrete, because steel has many advantages. It can stand axial loads, and it has quite high tensile strength, and therefore we can combine these two in order to have the advantages of these elements, and it therefore increases the strength. So we might have high strength concrete, which can stand both axial and basically compressive loads. One factor that we need to keep in mind is that we can increase the strength of both the concrete and the steel rebars. The yield strength of the steel can be increased to 3 times higher than the normal one when it is subjected to tension, and the yield strength of concrete in compression can also be increased 4 to 5 times higher than the simple ordinary concrete. So this means that we can have small cross sections, it can have longer spans, and also we might have less dead loads, and therefore we can save space, can save money, and also laboring. However, higher yield strength of steel means that it can be subjected to higher strains as well. If we look at the stress strain curve of the steels, the more stress we put on these steel bars, the higher strain we might have, and therefore higher stress, higher strains, and the higher strain means that we might have larger deflections and deformations and cracks, which is not desirable in most of the cases. And this has a limitation. So when it comes to the safety and serviceability of the concrete structures, most of the time, some specifications limit the basically yield strength of the rebars to be about 60 to 80 KSI, although it could be higher than 100 KSI. So we have codes and standards of using these concrete in our structures and in our infrastructure. So good. If we see pictures on the right side, and we say that we can have very high yield strength of the rebars, very high strength of these steel bars means more strains and more deflections. And more reflections means that we might have cracks and our beams, for example, the girders, they have like bridges, and it's somehow quite useful if we use this property of higher strength steels in the form of pre-stressed concrete. So we can use those high strength steel bars in pre-stressed concrete, and it means that steel in the form of wires, strands, or bars are embedded in the concrete under high tension. Then it becomes in equilibrium with compressive strength of the concrete after hardening. And most of the time we use pre-stressed concrete for flagellum members on tension side, much larger load than with not pre-compressed, and the pre-stressing reduces the deflection and the tensile cracks, and it increases the range of spans and types of structures. So then it comes the pre-stressed concrete story, and these pre-stressed concretes are used for mostly for flagellum members, basically the slabs and the beams. For example, if we need to have large spans of large span beams and slabs and a bridge, for example, we would better use the pre-stressed concrete. The way the pre-stressed concrete works is that first we make the forms and the molds, and then we add those high strength steel bars fixed at the end, and then we add the concrete, knowing that the fact that these steel bars are stressed, and they are in tension, and then this tension in these steel bars are becoming in equilibrium after concrete gets hardened. There are 3 stages for building these pre-stressed concrete, and this tensioning of tendons of steels, they have the anchoring at the end, so that these anchors and bolts can be used in order to connect these elements with other members of the building. For example, if there is a bridge, we can use these connections, for example, to connect the slabs or beams with the columns and the piers of the concrete bridge example. Let's go to another in the structural forms. As we said earlier, that concrete is shapeable. It means that we can have any type of shapes once we can create the desired forms, and it's easy to pour the concrete and get the desired shape, the desired structures. So there are various types of forms available for concrete structures. For example, in a building, in a high-rise building, we might have slabs and floors, and they are basically they have lower thickness and quite long sides, and we have unique forms for building the slabs and floors. For columns, we might have circular columns, or we might have rectangular columns, square sections, and for arcs, basically, which is also a unique form of the building element, and it can be used for bridges and curved slabs. Foundations, we might have footings of different types for piling, and for pile caps, we might also have make shapes and forms. And for moment-resistant frames, yes, basically we might have various types of forms for the beams and columns, for the bracing, and for other types of elements, which are like pipes, culverts, and it can also be a unique type of the structural forms. And for beam systems, we might have girders, beams, joists, and purlins, and for shell structures, sometimes we might have parabolic shapes, parabolic shells, hemispheric types. And for walls, we might have tapered walls, stack walls, composite walls of different types, and shear walls, retaining walls. So for domes, we might have cylindrical shapes, hemisphere shapes, and triangular, oval, segmental shapes. So imagine various types of forms, various types of regular and irregular geometric shapes, and of course, we can use the forms in those desired shapes and structures. Then using the concrete, covering the concrete, we can get the desired structures. And these forms and elements can be used, for example, in a building, we might have roof, slabs, floors, foundations, or mostly slabs. And for columns, might have various shapes, T shape, for example, or for the stairs, might have a combination of slabs and beams. For the walls, we might have various types of walls. And for the beams, we might also have various types. For the footings, we have various types of footings, like isolated foundation, wall foundation, and there are so various types of shapes and various types of forms available for each specific building element. It has to withstand the loads. We might have wind loads, we might have seismic loads, and overall we can basically classify these loads to three types of loads. Dead loads are constant in magnitude and fixed in location all the time. And dead loads or gravitational loads, which are permanent and attached to building, and they are part of the building. For example, weight of the columns, beams, which are all the time present and fixed in location and constant magnitude, they are dead loads. Live loads are variable and uncertain loads, and basically it changes over time. And they are also uncertain. That means that the frequency and the magnitude change over time as well, depending on the occupancy or the traffic load. If we see from residential buildings, for example, the occupancy is different. We might have various live loads during the life cycle of building. And for the bridges and concrete bridges, basically we might have traffic loads, which also changes over time. Sometimes we have higher traffic loads, and the peak hour, for example, we might have lower traffic loads. And they are sometimes minimum uniformly distributed live loads according to some codes and specifications. And they are statistically determined by engineers, and they are present in the building codes. We can use those available tables and graphs in order to determine the load of the building. And then we have environmental loads. For example, we have the snow loads, wind loads. Wind loads could be pressure and sanction. Might have seismic loads where buildings and infrastructures are located in seismic regions. And the temperature differentials also loads. If the temperature changes over time and the magnitude of this change is quite high, then this imposes basically load on building or element in types of basically tension and compression or expansion and compaction, and they change over time and magnitude depending on the local climate and the seismic condition. Let's go to another topic, which is also relevant to the first lecture, and it is serviceability, strength, and structural safety. When we design a building or an element, the very basic requirement is the structural safety. So it has to be safe enough in order to stand all the loads. It has to have quite high strength compared to the calculated loads, and it also needs to be serviceable. Serviceable means that the building should not be subjected to cracks of tolerable limits. When we consider the safety and serviceability, we need to consider the not only the calculated or the estimated loads, but also the uncertainties. So uncertainties are also important when we design the concrete structures, and construction codes determine various safety margins. The type of failures and consequences that building might have is also important. Buildings with lower occupancy, for example, which have lower consequence of failure, it might have lower safety margins. And the variability of loads means that maximum load on a building is not known. There is always uncertainty when we design concrete structures, or when we draw the curves for load, strength, and safety margin. The difference between the strength and load is called safety margin, and it should be always higher than zero. It means that the strength should always be greater than the loads on the structure. And these are random variables. So a strength also variable changes. The load also variable, therefore safety margin also variable. And therefore we add factor of safety for the strength, and we say the strength that we calculate for an element has quite uncertainty regarding the type of material, the way it's built. So we use a coefficient lower than 1 in order to account for this uncertainty, and then we add coefficient higher than 1 to increase the load on the building. For the building element subjected to only dead load, according to function 138, we have just one part on the right side, but if there is dead load and live load, then we might have various factors for the dead load and live load. And for the third function, we'll have dead load, live load, or snow load, wind load, and it also these are also variable and uncertain, but we as engineers have quite engineering judgment, as well as we do calculations in order to account these uncertainties and tolerable limit, considering the economy and the functionality of the buildings. Okay, let's go to one of the very important topic, and it's the design basis. Any building we design is based on a design philosophy. There are currently 3 design bases, have theoretical background that we use in order to design our buildings. The first one is the LRFD, or the design strength design concept for load and resistance factor design. So it is basically a load resistance factor design. This design philosophy comes from the fact that the actual strength of a member is important. And the computed forces in the members that we calculate in each element of the building should not exceed the design strength. And this design philosophy is based on a reliability, and we use probabilistic fundamentals and concepts in order to calculate the design strength as well as those forces computed in a building element. And therefore, the probability principles are added to the equations, and we not only calculate the probability of the strength and the forces, but also the probability of failure. Currently, most of the codes and most of the firms use this design basis for designing the buildings. The second one is service load design, and this design principle is used for in order to check serviceability of the concrete structures, and this comes from the idea that the maximum probable load during the lifespan of the structure is estimated. So we estimate the maximum probable load on a building, and then we say that this is the maximum load, and therefore each element should be designed accordingly. And the third one is allowable stress design, and this comes from the idea that the factor of safety is applied for the expected loads, and then compared to the material's capacity. Stresses in a structure should not exceed a specific allowable value. So the allowable stress design means that there is a unique stress, a unique strength and stress in the building element, and any load and those and any type of load that we impose on the building should not exceed this allowable stress. And it's basically when we build a bridge or any structure, and then we define the maximum number of people that should use maximum axle loads, and therefore we should care all the time, should take care of the users and the loads that are imposed to the building. And these loads should not exceed a specified allowable value that we determine for the building. To design the concrete structures, there are design codes and specifications, and there are various types of design codes. For example, we might have International Building Code or IBC. We can use these as guidelines for building design. In the United States, for example, buildings are designed according to ASI code, and the highways are designed according to AASHTO bridge design specifications. However, understanding the principles of structural mechanics and intermediate knowledge of the nature of materials are very important when we design these structures, and therefore a fair engineering judgment is essential. The codes and provisions are used as guidelines. So engineering judgment plus code provisions and understanding of the structural mechanisms, the nature of materials is they all together gives us the strength and the skills to design buildings that can stand the forces without any failures. The safety provisions of the ASI code is that strength reduction factors and load factors based on statistical information, experience, and engineering judgment. And these are basically saying that the design strength should always be equal and or greater than required strength. So we first calculate the design strength and the required strength, and then select the materials, sections, and elements in order to meet the required strength. And this then here is the nominal strength for the each element. And the required strength is calculated using load factors to the service loads. So we when we come to the specific forces, the specific stresses, there are various types. For example, this applies to the moment of in a building element, and this design moment should all be greater than the required moment in a building. And then it's also applicable to shear force, and shear force, the design shear force should be greater or equal to the required shear force in a building element, as well as the tensile strength should be greater or equal to than the required tensile load. And the last is the torsional strength should be greater than the torsional strength of a member. Let's go to the factored load combinations. We say that required strength U should be calculated, and according to the ACI code table 1.2, we have various load combinations based on the principal load. So first we see which principal loads are available. If there is only one dead load, 1.4 dead load means that it is the required strength. So we add 40% more, considering that the dead load in a building will be subjected to various uncertainties, and therefore we consider factor of 1.4 for live loads if it is present with the dead load, and then we have 1.2 dead load plus 1.6 live load plus 0.5 if it's a snow load or rain load, and various combinations are used for wind loads and for earthquake loads, as you see in the last two equations. And for the wind load, we have a maximum factor of 1. And for the seismic loads, we have component because it acts both horizontally and vertically. So we consider the vertical and horizontal components of the seismic load. If there are snow loads or any other loads, then we consider those as well. So on one side, we increases the required strength by adding those load factors, but also we reduce the strength of the elements. So we use reduction factors of 0.9 for tension controlled sections, and for various types we have various strength reduction factors. These all are because we want to have a safe, a serviceable, and a reliable structures. The joint application of the strength reduction factors and the load factors aimed at under a strength of 1/100 and overloads of 1/1000. This accounts higher level of certainties for the overload structures, members, and under strength. As we said earlier, the calculations of the strength and loads are always subject to uncertainties, and 1/100 for under strength members or 1,000 or loads members, quite good. And this results to the probability of structural failures on the order of 1 over 100,000. So the probability of structural failure is also quite low. 1 over 1,100 structures might be subject to failure if we use these fluid conditions. And in Australia, we have a national construction code for construction, and section 3.2.3 says that concrete must be manufactured to comply with Australian standard 3600. So Australia has its own standard for the concrete, and it must have a strength 28 days of not less than 20 megapascal. So the minimum strength for the concrete structures is 20 megapascals or and 20 grade after 28 days. And basically, it should not have aggregate size, nominal aggregate size greater than 20 millimeter. So 20 millimeter is the maximum aggregate size that we can use in a building. And it has to have a nominal 100 millimeter slam. So when we test, when we do the slam test, the nominal 100 millimeter is essential. And the materials used for reinforcing steel must comply with Australian standard 2870, and the minimum splice is 500 millimeter. And all reinforcement must be firmly fixed in place to prevent it moving during the concrete operations. So each rebar or each reinforcement that we use in a building, they should be firmly fixed in order to avoid movement during the concrete pouring. And the reinforcement must be supported off the ground or the furnace by board chairs made from wire, concrete, or plastic. So they should not be completely attached to the ground. And we always use board chairs in order to elevate those rebars because we need to have cover of at least 20 millimeters for the concrete elements. The last slide is about reference. As I told you, we use Reinforced Concrete Mechanics and Design 6th edition or 7th edition is also available. And we can recommend reading National Construction Code in 2022 and the Design of Concrete Structures 16th edition. As I told you, our references for preparing these slides and this lecture series. We might also use various pictures and various diagrams and figures from various sources. And yes, that's all for today. I hope you enjoyed watching these long lectures. If you have any questions or any suggestions, you can write in the comment. And if you like this video, you need to subscribe this channel so that you do not miss the other coming videos. And yes, this is the last days of 2024. Enjoy your holidays. A happy new year ahead. We'll continue this course next year. So the next year we might cover all the topics and the concrete structures. Thank you for watching. Have a nice day.